Let's start with a brief introduction. My name is Cecil Smith. My professional career spans almost 50 years and has been devoted solely to process control. Over the years, I have provided services to a variety of industrial companies. Based on these experiences, I have taught numerous continuing education courses, and I have authored 5 books published by John Wiley on various aspects of process control. The objective of this series of videos is to present the proportional integral derivative, or PID, control equation in the time domain. This is the language of process types such as chemical engineers. In academic process control courses, the typical approach is to express the PID control equation using S and Laplace transforms. Such expressions are even found in the manuals for some process control systems. Neither is necessary nor desirable. To convey an understanding of how PID truly works, the time domain is far more effective. To illustrate the various aspects of the PID control equations, the presentations will use a simulation of a hot air furnace. The schematic display presents the piping and instrumentation, or PNI, diagram for the hot air furnace. The hot air stream is produced by heating fresh air in the furnace. The source of heat is the combustion of fuel gas. The furnace contains a heat exchanger, so the products of combustion do not exit with the hot air stream. Consequently, combustion control is a separate issue. We are merely heating air. The furnace must supply hot air at the desired temperature. The temperature control loop adjusts the fuel valve opening so that the temperature of the hot air is maintained at or near its desired value. The loop must respond to changes in the set point or target for the hot air temperature. But in addition, the loop must also respond to any change that affects the hot air temperature. These changes are collectively referred to as disturbances and include flow or demand for hot air, fresh air temperature, fresh air humidity, etc. Transmitters are measurement devices that provide inputs to the process controls. The PNI diagram represents each transmitter as a circle enclosing a label, such as FT for flow transmitter, TT for temperature transmitter, and PT for pressure transmitter. The hot air process is equipped with 4 transmitters: fuel gas flow, fresh air flow, hot air temperature, and hot air pressure. A common final control element is a valve or damper outfitted with a positioning actuator. An alternative is a pump or blower outfitted with an adjustable speed drive, usually a variable frequency drive or VFD, but occasionally a steam turbine. The hot air furnace is equipped with 2 final control elements: fuel gas valve and fresh air damper. The PNI diagram also presents the control configuration. The hot air temperature loop is a simple feedback loop composed of a transmitter, a PID controller, and a final control element. The circle enclosing TC represents the hot air temperature controller. PNI diagrams can present varying degrees of detail, such as distinguishing between a control valve with a positioner and a control valve without a positioner. Simple PNI diagrams without such details suffice for our purposes. For process controls that rely on digital technology, the software is organized around function blocks. These are said to be configured, not programmed. For simple feedback loops such as the hot air temperature loop, A function block must be configured for each element on the P&I diagram. For the hot air temperature transmitter, a process variable, or PV block, must be configured. For the hot air temperature controller, a PID block must be configured. For the fuel valve, a valve block must be configured. Block names are not standardized. Most commercial control systems provide such blocks or their equivalent, but with a different name and somewhat different features. The simulator does likewise, using PV point in lieu of PV block and actuator point in lieu of valve block. The block diagram for a control configuration presents the required function blocks and their interconnections. In the next video, one will be constructed for the hot air temperature loop.